Thanks to the experimental work of George Simon Ohm, we know the relationship between voltage, current, and resistance. In his experiments, Ohm put together wires of increasing length and studied the relationship between voltage and current as the resistance grew due to the increasing length of the wire. Now, the end result, as we know, says the relationship between voltage, current, and resistance can be expressed in this form, and it's known as Ohm's law. Now, the experiment was done based on the conduction of electricity in metal wires, and metal wires are quote-unquote ohmic devices. So an ohmic device is any device that follows this law. Not all materials are ohmic. So you remember in the first semester of physics these two equations. The sum of all external forces acting on an object is equal to the product of mass and acceleration. Newton's second law of motion. And there's also Hooke's law that says the force exerted by a spring is equal to negative the stiffness times the deformation. It's a law that describes a ratio between stress in the form of force and strain in the form of deformation. Now, Newton's law is universal. This is true in all cases, whereas Hooke's law only applies to certain materials that remain within their proportional limit. So, in the same way, there are several laws that we encounter in this semester of physics. For example, voltage is the line integral negative E dot ds. That's a universally true expression. However, Ohm's law is not universally true. Now, for metal wires, it suggests we can solve for the current simply by dividing voltage by resistance. We can write Ohm's law in the form I equals V over R. Or if you prefer, I is equal to 1 over R times V plus 0. So it's in the form Y equals mx plus B. So that means an ohmic device, when expressed using a graph of current versus voltage, should give us data that makes for that trend line, right? Where the slope wouldn't be the resistance, rather would be the inverse of the resistance. Okay. That's as long as the temperature stays within a typical range. At extreme temperatures, we might actually see a graph that looks more like this. So as long as we stick to this range, the device is ohmic, but goes non-ohmic at extreme values of voltage. Okay, in other words, if we apply too great of a voltage, then the current grows up dramatically from there. No, actually, I think I have that backwards. I was thinking more of a graph of voltage versus current. I'm going to apologize. This represents something like the filament in a wire. So at really high voltages, so still have this idea that it can be ohmic within some range, but then deviate from this ohmic behavior. And yeah, the filament of a light bulb is like this. When the voltage gets really high, then the temperature starts to go up, right? The more current that results, the collisions between the electrons that are drifting and the impurities of the wire cause for a conversion of electrical energy into thermal energy. You get greater random vibrations of these molecules from repeated collisions, and that ends up making the temperature increase, but as the temperature increases, the resistance increases, and so we find that additional voltage doesn't give as much of a gain in current once the temperature gets too high, if that makes sense. I think we'll cover the temperature effect on resistance in one of the upcoming lectures. Then there are materials like diodes that are made out of semiconductor material. The symbol for a diode in an electrical circuit looks something like this, kind of intuitive. What it says is it can conduct a current very well in this direction. So if you apply a high potential here and a low potential here, no problem getting a current. However, when you reverse bias it, make the high potential this side and the low potential here, then you really don't get a current until you make that potential difference really large, and then maybe you can drive a current in the opposite direction. So we can think of the reverse bias or the reverse polarity as being the negative values on this voltage scale, and forward bias, an attempt to drive the electrical current toward the right, as being positive values on this voltage scale. So the way a graph of current versus voltage plots for these diodes, regardless of how large that reversed voltage is, you have almost zero current. Now in the forward bias, you get a very large increase in current with increasing voltage. And only if you get past a really large reverse bias that you can get any current to flow in the opposite direction. So this is very much non-ohmic behavior. So if you want to see all those graphs again side by side, here they are. Ohm's law holds up quite well for the ideal case of wires made out of metal under reasonable temperatures. Light bulb filaments reach extreme temperatures, and we can see the non-ohmic behavior at extreme forward or reverse voltages. And lastly, the graph of current versus voltage for the diode. So only the first case could we apply Ohm's law. So hopefully you understand what we mean by ohmic devices versus non-ohmic. Much of our study will be focused on the conduction of electrical currents through metal wires.